Okay, so today we are going to be talking about distributed systems. Does anybody have a guess what a distributed system means? It is kind of obvious from the name, but could anybody just take a guess of what a distributed system means in terms of computer science? Any ideas? Come on, take the two words, put them together. Anybody? No? Okay. Well, basically the concept is if you are working on a project, right, and you want to finish it faster, you basically get a team together, right? Because if you have more people working on it, you could basically finish it faster, right? So the same thing is true with computers, right? So if you have more computers doing the same thing, you could probably like finish the problem faster, right? So the whole point of distributed systems is to like combine a bunch of computers to get like more computational power, get more like storage space, all that good stuff. So that's what we're going to be talking about today. Okay. So here are just like some ways that distributed systems can help. You can see like these massive like trades of computers that like a bunch of like they really have stuff called like computer warehouses, right? So they basically have like a ton of these really big computers, and they all these computers are working together to finish stuff. And then you probably know that Amazon has like web services, and these are basically letting you use like all the computers that Amazon have, and they basically let you do a lot of computation on distributed systems. Okay, but there are some problems with distributed systems, right? Even though you get like all these benefits, right? You can speed things up. If one computer goes down, you have like 600 million more to actually do the rest of the computation, right? Also, they store data reliably, right? If one thing gets corrupted, then you have a bunch of other copies in other computers. And it's also consistent, right? If you want to double check that your computer's doing the right thing, you just double check its answers with other computers that are doing the same thing. But unfortunately, it's prone to failures, right? If you have like 100 computers, like your Mac, right? If you have a Mac, it's probably not going to fail that often, right? Like you could probably have it for 8 years without it like breaking down. But if you have like a million computers, one of them is bound to break at some point. Also, like just as if you're working with a team, right? If you have too many people working on the same project at the same time, nothing's gonna get done. So that's another problem with distributed system, right? Like the more people you have, you're not necessarily gonna get like twice as fast if you get like twice as many people. Same thing with computers. And then, of course, it is extremely painful to code. Coding in distributed systems is really nasty. Okay, so I'm just gonna do a couple of demos to show you guys how cool like parallelism is. So we're gonna do that on terminal. Does anybody know how to make uh, command run in the background on terminal? Does anybody know? Trivia points. Let's go. Anybody?
With an and, like you do, like you type your command and then type an and afterwards.
Exactly, right? So if I do like sleep 5, right? I have to wait 5 seconds before I could type my next command, right? But if I do sleep 5 and then put it in the background with an and sign, then essentially it just starts doing it, and I'll never see what happens because like I didn't tell it. Well, let's do sleep 5 and then echo done. Okay, how about that? Oh, I need to put parentheses. Sleep 5 echo done. And so now after 5 seconds, it'll do done, but I can still do other stuff while I'm waiting, right? So essentially, it's the reason why that works is because it's parallel, right? Basically, I'm doing something currently, but this other command is running on some other core of my computer. So essentially, if we have a multi-core computer, we could run like a bunch of these like background processes at the exact same time. So let us look at an example script, right? So this is basically my script, right? So it'll basically just it takes a start time, it does this thing 5 times, and each time it does 1,000 operations, and then it echoes done, or 100,000 operations. So 100,000 operations is pretty slow. So if I just like it, even though it's not doing anything, it's pretty slow. So if I just do /example.sh, you can see it takes like half a second for each one to finish, right? So what do you guys think will happen if I run all of these like 1,000 operations in parallel? What time do you think we're gonna get if each one takes around half a second? Any ideas? We're running them in parallel, people. What do you guys think? If all of these like 5 second or half a second, 500 millisecond tasks run at the same time, when will they all end? Come on, this is very simple. Let's go. Anybody? Okay, so if you are playing 10, okay, let's just say like there's like a violin part and a viola part, right? If you play the violin part and then the viola part, and it takes 5 minutes for each, obviously it's gonna take 10 minutes total. But why don't you put both of them together? You play both at the same time. Come on. Nobody's gonna answer. Please. It's not a hard question. Let's go. Nobody? Albert, tell me, please. I beg. Albert, you alive? Okay, fine.
Yes. It will just run in the background and you will be able to do everything else.
Yeah, but like, if all of these are running at the same time and each one takes half a millisecond, when will all 5 of them be done?
2.5 ms.
Well, that's what it does if you do it sequentially, right? But if they're all at the same time.
If you're doing it simultaneously, that makes sense. Then probably just 0.5 ms.
Exactly, right? So essentially, instead of taking 2.5 seconds, we could actually speed it up to only 0.5 milliseconds, right? I mean 0.5 seconds. So let's try that. And you can see, right? Everything finished. See, all 5, 1, 2, 3, 4, 5, all finished in less than half a millisecond. So that's like a 5 times speed up, right? So that's pretty cool, right? Just by making everything run at the exact same time, we could get a really, really fast program. Unfortunately, Yusuko did not let you use parallelism because that would be kind of broken. They only run your code on one core, so you can't like make your thing faster by doing this. But you can speed up a lot of things by like putting things on different cores of your computer and making them run at the same time. Okay. So making things run in parallel is pretty easy, right? On Bash, you just put an and next to it, and then they'll all run at the same time. But what happens if they depend on each other, right? So like take this Go code for example, right? Like you have a counter and you're basically finding the sum of the squares from like 1 to n, right? So like I think so basically like this seems pretty straightforward, right? Like if I just run this, it'll finish pretty fast. So let's try it. Oops. Okay, so let's go concurrency.go. Oops, go run concurrency.go. Okay. So it basically took so basically it takes 2.5 seconds in order to run the sum of the first 5 squares. Basically I put like a sleep here just to pretend like it takes half a second to find each square, right? Okay. So basically it found that the sum of the first 30 squares is that. What happens if we try to make it concurrent, right? We want to make it run at the exact same time. Okay. In Go, does anybody know how to make things run in the background in Go? It's kind of big brain. Any guesses? No? Okay, you literally just put Go before it, right? So now if I do this, it'll basically take only if I do this. Okay, it didn't even work, right? It basically like stopped immediately after, like it stopped and it said the first 0 squares are 0, right? So does anybody have an idea why this is? Does anybody know why it suddenly just stopped? Okay, well, the reason for that, I should probably do this and do that, is because essentially it's stopping before all of the all of the threads are done, right? So essentially we could prevent that by doing sync, and we could do a wait group. So var sync.wait group, and we could basically just do wg.add1 wg.wait. So essentially this is just making sure it waits until all of them are done. So then we could do wg.done. Okay. Okay. Whoops. Alright, so you can see we sped it up by 5 times and it still found the sum of the first 5 squares pretty easily. Okay. What happens if we try to find the first, like, I don't know, what's a big number? Somebody give me a big number. Anybody have an idea? No one wants to give me a big number? Okay, we'll just do, how about like that? Okay. Oops, I should probably also take out the sleep thing so that it is faster. Actually, this might take a while. Okay, maybe I should do a smaller n. Okay, yeah, let me make a smaller n. Hold up. Okay. Wait, oh, let me stop printing because printing takes a while. Okay, so it found it in literally the same amount of time, right? I made it way bigger, but it still took the same amount of time because we're using parallelism, right? So essentially we get that the sum of the first that many squares is that, but if we run it multiple times, it gives us a different answer each time. Wait, that seems wrong, right? Why are they giving us different answers? So why don't we think about that? Okay, so does anybody know why it might be giving us different answers if everything's running at the same time? So just as a hint, if you do if you're adding something to something, it first reads it, then it calculates x plus 1, and then it stores it. So how could it be possible that some things don't get added? Does anybody have an idea? Okay, let's just say we're adding 1 to like a counter, right? So two guys are trying to add 1 to 0, right? So the right way to do it, right, is one guy reads 0, and then he adds 1, and then he puts it back, and then the next guy reads a 1, and then adds 1 and puts it back, right? But what happens if one guy reads a 0, and the other guy reads a 0, and then what happens? What will your x be at the end of that? If they both read a 0? Any ideas? Come on, if they both read a 0, what are they going to calculate for x plus 1, and what are they going to store? Nobody? Did I get something in chat, maybe? Hey, very nice, right? So they're going to store it to 1, right? Even though we're adding 1 twice, we're still only getting 1. So apparently the computer thinks that 0 plus 1 plus 1 is equal to 1. Very nice. But we could fix that, okay? Like, basically these are called race conditions, right? So essentially, if you're incrementing something by twice, right? Thread A might read it 17, and then they both get 18, and they both write 18 instead of getting 18 and writing 19, right? So if we want to stop that from happening, so essentially we could lock it, right? We could only let one thread edit it at a time. So we're going to use something called a lock. Okay. So essentially it's called a mutex, so what we'll call it var lock is think.mutex that basically sounds like mutually exclusive lock, which means only one guy could do it at a time, right? So essentially right before we edit this, we gotta do lock.lock and lock.unlock. Okay, let's try that. Okay, it went faster somehow, but it should always give us the same answer now, right? Because everything is getting added correctly. Okay, very cool. So that's another thing you have to worry about with distributed systems, right? Because basically if multiple things are doing it at the same time and they try to edit it at the same time, you might have those weird race conditions. So that's cool. Okay. Also, just to show a difference between the concurrent thing and non-concurrent, if we took out the parallelism, then it'll be very slow. Okay. Hold up. Okay. Whoops, I missed one thing. Okay. See, wait, what? 2. Okay, wait. Maybe it was a bit slow because of the lock, but basically the idea is if you do things parallel, it's a lot faster. Okay. So next thing, MapReduce. So I think a lot of you guys have heard about MapReduce, but basically what's cool about MapReduce is that it lets you put stuff on distributed systems pretty easily, right? Like I think the main problem with distributed systems is that it's really hard to code stuff for distributed systems. So essentially MapReduce basically gives you basically you don't have to figure out all the nonsense we did in Go. Like it'll automatically do it for us, and all we had to do is come up with a way of doing something. So essentially, MapReduce is basically just a way of approaching a problem. So it splits the problem up into 2 parts. Map takes in an input and spits out a bunch of key value pairs. Let's just say, theoretically, we wanted to find the word count for each word in a text file, right? Then basically what map would do, it would take in a line of text, take the words in the text, and then spit out a word comma 1 for each of them, right? So then now we have a bunch of these key value pairs, and reduce basically takes all the ones with the same word and combines them, right? So essentially, if we had like two like Alberts, right, in our text file, then essentially the reduce function will see, oh, we have two Alberts, and it can combine them together, and now it'll say Albert has Albert comma 2, right? Albert has 2 occurrences. So that's the basic idea behind MapReduce, right? You basically want to find a way of solving your question by having a map function that takes an input and creates the pairs, and then a reduce function that takes in all the pairs of the same type and gives you an output for that particular pair, right? So we're going to do a real quick coding demo. Does anybody know who made Spark Reduce? Like trivia, computer science trivia. Does anybody know who made the concept of MapReduce? Nobody knows. Come on, people. I kind of gave a hint. No? Okay, well basically it was made by Hadoop, and then like Apache Spark made their own like library for it, so it's pretty cool. And basically we're just going to be using like Scala to demonstrate this. So the first step in this is to once it's done loading. Okay, so first we're going to read up the text file. So val text file is equal to sv.textfile, and then the name of the text file we want to do. Okay. Then essentially what we want to do is we want to split it up into words. So we'll do like we do dot flat map line to line dot split, and that basically just splits it up into words. And then if we store this in like val split, and we do split dot collect, you can see, right, it basically has an array of all the words in our document. Very cool. Okay, so we got our words in our document. Then what was the first step in our MapReduce thing? What should we do first? Come on, guys, MapReduce is pretty cool if you guys like try to like think through it. So come on, what's the first step? Nobody? Okay, well basically the first step is we gotta map it to our key value pairs, right? So the key was the word and the value was just the one. So if we take split, or we'll do val map result is equal to split dot map, and then we want to take in each word and we want to map it to like, I don't know, a tuple of word comma 1. Okay, very nice. And then what do we do after the map? Anybody have an idea? No ideas? Okay. So we'll do val reduce result is equal to split dot reduce, and we'll take in the value, or we'll take in 2 values and we'll just sum them up, right? Because if we have like 3 comma, we currently have 3 and we get a word comma 1, we want to add 1 to our total, right? So we just do a plus b. A plus b. All right. And then at the very end, all we got to do is reduce result dot collect. Oh, whoops, I did that wrong. Okay, hold up. Val reduce result is equal to split reduced by key. Whoops. Like that. Whoops, map result. Okay, there we go. Okay, so now we basically have our reduce result, and once we do the reduce result, we should be done. So we just do reduce result dot collect, and hooray! You basically see we got word counts for all of these dudes. It's very epic. Okay, so let us go back to the presentation. Alright, so let us think of some MapReduce algorithms. I don't think you guys have been really, you guys are interested in this that much, but if you guys want to, does anybody have an idea for how we might do this? So essentially we have a database of 1 billion people, and we want to compute the average number of contacts a person has according to age, right? So what are the first steps? Anybody? No? Okay, well basically the first step is you want to figure out the map step, right? You want to be able to group them into, you want to put out a bunch of key value pairs so that you can group it by the key, right? So what do we want to group by? We want to group by the age, right? Because we want to find the average number for each age, right? And then what do we care about each person? Well, basically we care about their social contacts, right? We want to know their number of social contacts. So basically what your map does is it spits out your age as the key, and then the number of contacts, comma 1, right? Like 1 is how many how many people this tuple stands for, right? And then essentially we reduce these into like a tuple that keeps track of like the total number of contacts and the total number of people, right? So basically our reduce function becomes adding up the number of ones and number of contacts and then just dividing the average, right, for a particular key value pair. Okay, so just some easier ones. If you wanted to find how many words of each length there are in a file, you could literally just do the same thing that we did for the other one. Like if we took our map result, or no, if we took our split and we mapped it, right, and instead of doing from word to word comma 1, we can actually map it to word.length comma 1. So now we could group up all the things by their length, right? So word.length comma 1, and then we just do dot reduce by key, a comma b, a plus b, and dot collect. Okay, and very nice. We basically have all of these. Let us actually like sort it so it's a bit nicer. Util dot sorting dot quick sort. Whoops. And then, okay, we had okay, hold up. So we'll sort results. And then we could do this to result. So we do that, and then we just do result.collect, or results, actually. Then hooray, you basically have, there are 73 0-letter words, there is one 16-letter word, there are two 73-letter words, and so on and so forth. So very nice, okay. And then essentially, given a list of friend pairs, find out how many common pairs. This one's kind of hard, but if you guys want to try it out on your own, it would be pretty cool. Okay, so just as a refresher, like MapReduce basically like takes care of all of this for us, right? We don't even have to think when we write MapReduce. Once we have a MapReduce, we could put it on distributed systems without doing any code of our own. All we do is write whatever I was doing in terminal, and that was pretty easy, right? Like it's only like one line of code. So essentially, it'll take care of sending the app code to the servers. It'll take care of keeping track of which tasks are done. It'll take care of moving data from maps to reduces. It'll take care of load balancing, right? Like you don't want one machine doing all the work. This will make sure that all the machines are doing equal amounts of work and it happens as fast as possible. And then if one of the machines shuts down, then your like MapReduce could just send it to a different machine and it'll do it for you. Okay, then just some other concepts that are kind of cool. Basically, distributed systems, they talk to each other using something called remote procedure calls. And the reason why these are really cool is because it makes it super easy to actually code these things, right? Like all you have to do is you just have to write one method on the server and then you're done. Then also there is transactionality, right? Like you want to deal with race conditions, but between different machines. And there's consistency, right? Like what happens if one guy dies, right? Like I think on the next slide I have an example of this. So let's just say like, I don't know, like this client tells this agent, okay, let's update this like x equals 0, update that to x equals 1, right? But then when it's sending the information to the other agent, the message gets deleted, right? Like the message doesn't reach the other agent. Then then basically this guy has 1 and this guy has 0, 0. So if clients like talk to these guys, they'll get a different answer than if they talk to this guy, which is not good, right? So that's another like issue that people have to deal with for databases or distributed systems. And then of course, logically, if you think about it, right, if multiple things are running the same code, if one goes down, there are others to replace it, and that is called fault tolerance. And you know, like Amazon, right, it's always up, right? Basically, the reason why that is because they have such a cool distributed system model, right? So basically, they have 3 availability zones, and within that, they have replications, 2 replications per availability zone. So essentially, even if one whole like data center goes down, there's still like replication in another data center that they could get it from. And even if one whole data center and like one of these replications goes down, there's always going to be at least one other copy of the data. So essentially, there's literally no way for you to lose your data unless they like destroy 2 entire like data centers. It's pretty cool. Okay. So that is all we got for today. Let me put the flag in the chat. I put a couple challenges on the website if you guys are interested. Distributed systems are pretty cool, so you guys should probably try it out. MapReduce is kind of fun if you actually like think through the problems. But other than that, that is all we got for today. So remember, if you guys have any questions about UseGo, let me know down in the or